Hello and welcome to Deep Scienced Sleep. I'm delighted you've joined me. Tonight, we will embark on a tranquil journey through the dynamic systems above us, uncovering the intricate science of weather. Those gentle zephyrs, rumbling thunderclouds, delicate snowfalls, and sun-drenched afternoons collectively form the ever-shifting temperament of our sky. Consider this your personal invitation to float effortlessly among the clouds, all while remaining snug and comfortable in your own space. A gentle note. While this presentation is crafted to help you unwind and transition into rest, it's possible the fascinating details might just capture your attention. Should you find yourself wide awake at 2 a.m., contemplating cumulonimbus clouds and the Coriolis effect, you'll at least be a little wiser for it. Before we begin, I'm curious to know, where in the world are you listening from? And what time is it for you right now? Whether you're tuning in at midnight, dawn, or any hour in between, your presence here is a pleasure. If you enjoy these serene, curiosity-filled explorations, please consider liking this presentation and subscribing to the Deep Science Sleep channel. Your support helps our community grow, allowing more inquisitive minds like yours to drift into slumber enriched with gentle wonder. A quick reminder, while we'll discuss temperature, pressure, and other elements that might relate to how your body experiences weather, this content is strictly for educational and entertainment. It is not a substitute for professional medical advice. For any health concerns, particularly related to temperature extremes, please consult a qualified healthcare provider. So, if you wish, close your eyes, release the tension in your shoulders, and take a long, soothing breath. Tonight, we explore the mechanics of weather, the science behind every raindrop, rainbow, and rumble in the heavens. Let's begin. We start with something ever-present yet often unnoticed: the air. We reside at the bottom of an invisible ocean of gases, a vast, gently undulating sea we call the atmosphere. Unlike aquatic oceans, we don't need special gear to breathe this medium, though it can playfully tousle hair or send papers flying. The atmosphere is the grand stage where all weather performs. Proportionally, its thickness is comparable to the skin of an apple relative to the fruit. Most of it clings closely to Earth in a relatively shallow band. If you've ever gazed from an airplane window at 35,000 feet, you've ascended above a significant portion of it. The atmosphere is structured in distinct layers, each with its own character, like the strata of a cake, though far less palatable. The lowest layer, where all the weather we experience occurs, is the troposphere. This is where clouds assemble, rain descends, and winds engage in their playful mischief. The troposphere extends roughly 7 miles high on average, though it's deeper at the equator and shallower near the poles. Above lies the stratosphere, home to the ozone layer, Earth's natural sunglasses, shielding us from the sun's more assertive rays. Ascending further, we pass through the mesosphere, where meteors incinerate in brilliant streaks. Higher still is the thermosphere, a realm of auroras and satellites, where temperatures can soar to thousands of degrees Fahrenheit. Yet it wouldn't feel hot due to the near vacuum conditions. At the outermost fringe, blending into space, is the exosphere, a whisper-thin boundary where molecules are sparse and often drift into the cosmic void. But for now, let's remain cozy within the troposphere, our home layer. The air here is primarily nitrogen, constituting about 78% of the mix. Oxygen accounts for approximately 21%. The remainder is a cocktail of trace gases like argon, carbon dioxide, and a variable amount of water vapor. It may not be the most glamorous blend, but it's perfectly suited for life as we know it. Now, let's consider how air behaves, for this is where things become intriguing and dynamic. Air is a fluid, much like water. It flows, swirls, and tumbles, critically responding to changes in temperature and pressure. Warm air tends to rise due to its lower density, while cold air sinks because it's denser. This fundamental principle, warm air up, cold air down, is the very pulse of weather. When sunlight reaches Earth, it doesn't heat the surface uniformly. The equator receives abundant solar energy, while the poles get much less. Land warms faster than water, mountains are cooler than valleys. These disparities create pockets of warm and cold air. Since nature strives for balance, the atmosphere perpetually attempts to equalize these differences. Imagine a sunlit patch of ground. As the sun warms it, the air above begins to rise. As it ascends, it cools. Cooler air has a reduced capacity to hold moisture, so any water vapor within that rising air condenses into minute droplets, forming clouds. Meanwhile, surrounding cooler air rushes in to fill the void. This movement is convection, the same process that circulates heat in an oven or bubbles in boiling soup, albeit on a vastly grander scale. Now, let's discuss pressure. Air possesses weight, not much individually, but collectively. The column of air above you exerts about 14.7 pounds per square inch at sea level. That's akin to a small cat gently pressing on every square inch of your body simultaneously. We term this atmospheric pressure, and it fluctuates with altitude and weather conditions. High-pressure systems are like serene, weather-stable, calm, often bringing clear skies as air gently sinks, discouraging cloud formation. Low-pressure systems, conversely, are more energetic. Air rises here, fostering cloud development and frequently leading to rain or storms. The pressure difference between areas generates wind. As air moves from high to low pressure to equilibrate, it's a form of atmospheric tidying, though often a messy one. And because Earth rotates, spinning at over 1,000 mph at the equator, this air movement is deflected. This deflection is the Coriolis effect, causing winds to curve as they travel, to the right in the northern hemisphere and to the left in the southern. It's one of those delightful physical quirks that seems magical, but is simply physics in action. Incorporate moisture, topography, and time of day, and you have a recipe for perpetual motion. The atmosphere is in constant flux, never identical from one moment to the next. Even on a tranquil, cloudless day, subtle air currents glide past, humidity shifts imperceptibly, and temperature gradients perform their invisible dance. It's a system not merely alive, but vibrantly lively. What's truly elegant is that this entire swirling, ever-changing engine operates without any central control. It is self-organizing, driven by physics, gravity, and the fundamental tenets of thermodynamics. Energy disperses, heat moves from warmer to cooler regions, pressure seeks balance, water evaporates, falls, and evaporates again. The atmosphere strives for equilibrium, a state it rarely achieves, yet never ceases pursuing. And that is the essence of weather. Earth is a restless sphere, enveloped in gases, dancing with sunlight and spinning through space. Every gust, every cloud, every raindrop is part of this continuous quest for balance. So, the next time you observe clouds scudding across the sky or feel a breeze ruffle your hair, recognize that these are not random motions. They are part of something vast and magnificent. An ancient, invisible ballet choreographed by sunlight and stirred by gravity. And it all begins right here, in the air we breathe. The sun, though approximately 93 million miles distant, is the ultimate conductor of our planet's weather. Without it, Earth would be a frigid, dark rock devoid of wind, clouds, or weather applications, alerting us to showers that somehow always drench our socks. Solar energy is the predominant driver of all weather. It arrives as sunlight, technically electromagnetic radiation, warming Earth's surface. But here's the first nuance. The sun doesn't heat the atmosphere directly. Instead, it warms the ground, oceans, and surfaces, which in turn heat the air above them. So, it's not sunshine directly warming the air, it's Earth radiating heat upward, akin to a stovetop heating the air once ignited. Not all regions absorb sunlight equally. Due to Earth's spherical shape and axial tilt, some areas receive concentrated solar radiation, while others get a diluted amount. The equator, for instance, receives more direct sunlight than the poles. This creates a persistent thermal imbalance. The tropics warm significantly, while polar regions remain cold. And when imbalance arises, nature acts to smooth it out. The result is motion constant, beautiful atmospheric motion. Warm air near the equator rises, creating a low-pressure zone at the surface. Air from higher pressure regions flows in to fill the gap. Meanwhile, the rising air moves aloft, eventually journeying toward the poles, cooling en route. At higher latitudes, the air descends and begins flowing back toward the equator near the surface. This large-scale circulation is a convection cell. Given Earth's size and our penchant for naming, we identify 3 primary convection cells in each hemisphere. The Hadley cell nearest the equator, the Ferrel cell in the mid-latitudes, and the polar cell near the poles. Together, these cells redistribute heat from the equator toward the poles, maintaining atmospheric circulation like a colossal, invisible conveyor belt. Within these cells, major wind systems emerge. Near the equator, the trade winds, steady easterlies blowing from east to west, prevail. Sailors historically relied on these winds for ocean crossings, sometimes leading to unintended discoveries. If you've ever pondered how new lands were accidentally found, trade winds are a significant factor. Further from the equator in the mid-latitudes, we encounter the westerlies, blowing from west to east. These winds propel weather systems across North America and Europe. Closer to the poles, the polar easterlies, cold, dry winds blowing from east to west, dominate near the Arctic and Antarctic. These wind patterns would travel straight if Earth were stationary. But here enters the next twist, the Coriolis effect. Because Earth rotates, any object moving over its surface, including air, is subtly deflected. This isn't due to whimsy, but physics. Earth rotates fastest at the equator and slower near the poles. Air moving between latitudes carries its rotational momentum, causing deflection, rightward in the northern hemisphere, leftward in the southern. The Coriolis effect doesn't cause dramatic spirals like a flushing toilet, but over extensive distances and durations, it profoundly influences wind patterns. It's why cyclones spin counterclockwise in the northern hemisphere and clockwise in the southern, and why global winds form consistent bands rather than chaotic tangles. Zooming out further, we encounter another powerful influence, the jet stream. Jet streams are narrow, high-altitude ribbons of fast-moving air, meandering at boundaries between major air masses. The most renowned is the polar jet stream, flowing between cold polar air and warmer mid-latitude air. It typically resides 6 to 9 miles above the surface, reaching speeds exceeding 200 mph faster than most sports cars, and thankfully with fewer tailgaters. Jet streams form where strong temperature contrasts exist, acting as atmospheric rivers that steer weather systems across continents. When a jet stream dips or ridges, it can induce cold snaps, heat waves, influence storm development, and either delight or vex forecasters. They also impact aviation. A west to east flight often benefits from a jet stream tailwind, shortening travel time. It's the atmospheric equivalent of a moving walkway, only vastly swifter. But Earth isn't just rotating and warming. It's also tilted approximately 23.5 degrees. This tilt gifts us seasons. As Earth orbits the Sun annually, different hemispheres receive varying amounts of sunlight. When the northern hemisphere tilts sunward, it experiences summer longer days, higher sun angle, more concentrated energy. Simultaneously, the southern hemisphere tilts away, experiencing winter. 6 months later, the roles reverse. During equinoxes, both hemispheres receive roughly equal sunlight. This shifting solar distribution alters global temperature patterns, affecting wind systems, storm tracks, and ocean behavior. Speaking of oceans, these vast blue expanses covering over 70% of Earth's surface are not passive. They absorb immense solar energy, storing it like thermal batteries. Water heats and cools more slowly than land, which is why coastal regions often enjoy milder climates. Oceans also circulate. Major currents like the Gulf Stream or the Kuroshio transport warm water across great distances, helping regulate climate. When ocean conditions shift significantly, such as during El Niño or La Niña events, they can trigger global ripple effects on rainfall, drought, and temperatures. So, to recap, without leaving your cozy refuge, you've now journeyed through the intricate choreography of Earth's weather engine. The sun heats the planet unevenly. That heating prompts air to rise and fall. Earth's rotation deflects this air into graceful curves. Jet streams ferry it across the sky like high-speed ribbons. And planetary tilt ensures no region remains static for long. The result is a world where no 2 days are truly identical, where the wind on your cheek, the drifting clouds above, and the rain pattern on your window are all part of the grand planetary ballet, powered by sunlight and sculpted by motion. It's a delicate equilibrium, playing out over billions of years. And all of it, from the faintest breeze to the most violent storm, originates from the sun's distant, nurturing touch. Moisture in the air often goes unnoticed until it affects hair or fobs glasses. Yet, this invisible water vapor is central to shaping global weather. It generates clouds, produces rain and snow, and fuels storms. It's also responsible for some of the sky's most stunning and dramatic scenes. In essence, moisture is the atmosphere's secret ingredient, ever present, even under seemingly clear skies. Let's start with humidity, a term for water vapor in the air. Water vapor is water in gaseous form, and air's capacity to hold it depends on temperature. Warm air can retain more vapor, cold air less. This is why summer days can feel muggy and tropical, while winter air often feels crisp and dry. It's not imagination. There genuinely is less moisture in cold air. Meteorologists typically reference 2 humidity types, absolute and relative. Absolute humidity denotes the actual vapor content, like 12 grams per cubic meter. Relative humidity, more expressive, is a percentage comparing current vapor content to the maximum possible at that temperature. At 100% relative humidity, the air is saturated, condensation is imminent, and dew, fog, or clouds form. You've likely experienced this on a hot day. Even without saturation, high relative humidity feels sticky because sweat evaporates less efficiently, hindering your body's cooling mechanism. In contrast, dry air facilitates rapid evaporation, leaving you cooler, if somewhat desiccated. Now, consider clouds. These soft, lofty sky blankets appear light but comprise countless tiny water droplets or ice crystals. Each droplet is minuscule, about 1 million combine to form a single raindrop. Despite their ethereal appearance, an average cumulus cloud, the fluffy type children draw, can weigh hundreds of thousands of pounds, comparable to a jumbo jet, seemingly defying gravity. How do clouds form? It begins with evaporation. Water from oceans, lakes, rivers, and damp soil heats up, transforming into vapor. This vapor rises because warm air is less dense and more buoyant. As it ascends, air pressure decreases, the air expands and cools. Cooler air can't hold as much vapor, so the excess condenses into tiny droplets or ice crystals, clinging to microscopic particles like dust, salt, or pollen. These are cloud condensation nuclei, the seeds for cloud formation. Different cloud types arise from varying ascent patterns and moisture availability. Gentle uplift creates stratus clouds. Flat, gray layers often associated with overcast gloom. Rapid ascent forms cumulus clouds. Fluffy cotton balls. Under unstable, moist conditions, cumulus can grow into towering cumulonimbus, the giants that power thunderstorms. Other cloud varieties include cirrus high-altitude wisps of ice crystals, often feathery and signaling approaching fronts, lenticular lens, shaped clouds over mountains, resembling UFOs, and mammatus, pouch-like formations pendant from storm clouds. There's even altocumulus castellanus, resembling a parade of tiny turrets. The names may sound arcane, but they belong to a precise atmospheric lexicon. Once a cloud forms, precipitation doesn't necessarily follow immediately. Cloud droplets must grow sufficiently to overcome air resistance and fall. This occurs through coalescence, droplets colliding and merging into larger ones. When they reach about 2 mm, they fall as raindrops. In cold clouds, the process may involve ice crystals accumulating moisture until they descend as snow. Interestingly, raindrops aren't teardrop-shaped. Air resistance flattens them into hamburger bun forms. Excessively large drops can split during descent. Precipitation isn't solely liquid. When temperatures remain below freezing from cloud to ground, snow results. Snowflakes form when vapor freezes directly into ice crystals, their shapes dictated by temperature and humidity, needles, plates, or the classic 6-armed stars. While no two snowflakes are exactly identical, this is more statistical probability than poetic license. With quintillions of flakes, some are bound to be similar. If air near the ground is above freezing but the cloud is cold, snow may partially melt into sleet, refreezing before impact. Or freezing rain may occur. Liquid rain that freezes upon contact with cold surfaces, creating treacherous ice glazes. Then there's hail, distinct from frozen rain. Hail forms in robust thunderstorms with powerful updrafts. A small ice pellet is cycled through the storm, collecting layers of supercooled water that freeze on contact. Each ascent and descent adds icy strata until the hailstone becomes too heavy for the updraft, plummeting to earth. Hailstones range from pea-sized to softball-sized, the latter fortunately rare. Water doesn't always fall. It can condense on surfaces as dew, those glistening droplets on morning grass. Dew forms when the ground cools overnight, chilling the adjacent air to its dew point, prompting condensation. If temperatures drop below freezing, dew becomes frost, adorning surfaces with intricate ice patterns. All this moisture movement, evaporation, condensation, precipitation, comprises the water cycle, nature's perpetual recycling system. water evaporates from surfaces, rises, forms clouds, falls as precipitation, and returns to waterways, repeating the cycle over billions of years, essential for all life. Air needn't be still for clouds and rain. Fronts, boundaries between air masses often trigger weather changes. When warm, moist air encounters cold, dry air, the warm air is forced aloft, initiating condensation, cloud formation, and frequently rain. Thus, many weather shifts commence with a passing front. So, the next time you gaze at a cloud, see it as more than a floating puff. It's the visible manifestation of an intricate interplay of temperature, moisture, and motion occurring all around you. Every droplet, every misty wisp, every sudden shower participates in this grand aqueous dance overhead, all originating from unseen atmospheric moisture. When the atmosphere hosts a celebration, thunderstorms are its pyrotechnics. They rumble, flash, deluge, and sometimes hail walnuts at rooftops. Despite their drama, thunderstorms simply result from air, water, and electrical flare, a meteorological cocktail with a vibrant garnish. Formation begins with warm, moist air rising into cooler air above, an updraft typically initiated by surface heating. Imagine a hot summer afternoon. Sun-baked ground heats a surface air pocket, which, being lighter, ascends. As it rises, it expands and cools. If sufficiently moist, it eventually reaches its dew point, the temperature where vapor condenses into droplets. This condensation releases latent heat, providing additional uplift, like rockets on a balloon. A cloud develops. Initially an innocent cumulus, but with ample moisture and instability, it can evolve into a towering cumulonimbus, stretching up to 10 miles high, surpassing Mount Everest. Inside, chaos ensues. The updraft thrusts warm air upward, while gravity pulls cooled air and precipitation downward in a downdraft. This vertical motion powers the thunderstorm engine. Thunderstorms progress through 3 stages: cumulus, mature, and dissipating. The cumulus stage involves rising air forming a cloud, steady and quiet. The mature stage introduces noise, vertical growth, rain, lightning, and thunder. Updrafts and downdrafts coexist in a turbulent dance. Finally, the dissipating stage sees the downdraft dominate. Rain cools the surface, cutting off the warm air supply, and the storm gradually collapses. The dramatic centerpiece is lightning, nature's method of balancing electrical charges with flare. As the storm churns, ice crystals and droplets collide, becoming electrically charged. Lighter ice particles gain positive charge and rise. Heavier hail and drops become negative and sink. This charge separation creates immense voltage differences, millions of volts, between cloud regions or between cloud and ground. Eventually, the air succumbs to a discharge, lightning. The process starts with a step leader, an invisible, zigzagging path of charged particles descending from the cloud. Nearing the ground, the electric field intensifies, prompting a streamer to ascend from the ground. Upon connection, a powerful current surges, producing a brilliant flash, lightning. The lightning channel heats to about 50,000 degrees seconds, 5 times hotter than the sun's surface. This rapid heating causes explosive air expansion, generating a shock wave we hear as thunder. Light travels faster than sound, so lightning is seen before thunder is heard. To estimate distance, count seconds between flash and rumble, divide by 5 for miles. E.g., 10 seconds equals 2 miles. Lightning varieties include cloud to ground, most dramatic and hazardous, intracloud within a single cloud, and cloud to cloud between storms. Exotic types include ball lightning, glowing orbs still enigmatic, and sprites and blue jets, high-altitude electrical phenomena shooting into the mesosphere. Sprites, resembling red jellyfish, occur above large storms and were once dismissed as pilot hallucinations, but are now confirmed. Lightning is potent. A single bolt can carry over 1 billion joules, capable of powering a small town momentarily, igniting wildfires, damaging structures, and proving fatal. Hence the adage, "When thunder roars, go indoors." Thunderstorms also produce hail, formed in strong updrafts as water droplets are carried aloft, freeze, and are repeatedly lifted, accumulating icy layers until too heavy to remain airborne. Hailstones range from pea to softball size. Wind is another feature. Downdrafts create gusty winds that spread upon surface impact as downbursts, sometimes mistaken for tornadoes. Speaking of tornadoes, some thunderstorms spawn them, particularly supercells, storms with a rotating updraft or mesocyclone. This rotation stems from wind shear, varying wind speed direction with height, creating horizontal spin-tilted vertical by updrafts. If the mesocyclone tightens and extends downward, a funnel cloud may form, becoming a tornado upon ground contact. These are rare, but among Earth's most violent phenomena. Most thunderstorms are simpler, brief energy releases forming clusters or along fronts, especially cold fronts where advancing cool air lifts warm, moist air. An associated phenomenon is the gust front, the leading edge of cool air from a storm's downdraft, lifting warm air ahead and potentially spawning new storms in a chain reaction. Despite their ferocity, thunderstorms are common. Approximately 2,000 occur globally at any moment. They are vivid reminders of our atmosphere's dynamism. Brief, potent expressions of natural energy, temporary disturbances in the atmosphere's endless pursuit of balance. When lightning illuminates the sky and thunder growls, it's the sound of atmospheric tension release, one electric exhale at a time. When the atmosphere intends to make a statement, eschewing polite breezes and showers for grand spectacle, it unleashes tornadoes and hurricanes. These mighty tempests headline Earth's meteorological theater. Swirling masses of raw energy capable of scarring landscapes and reshaping coastlines. They are loud, powerful, and often terrifying. Yet beneath the fury, they obey the same principles governing all weather, air, moisture, pressure, and motion, simply amplified. Let's begin with tornadoes, rotating air columns extending from thunderstorm bases to the ground. They are short-lived, often minutes, but can be astonishingly intense, boasting the strongest surface winds recorded, over 300 mph, exceeding Formula One speeds. Tornadogenesis isn't fully understood, but key ingredients include a potent thunderstorm, usually a supercell with a rotating updraft or mesocyclone. This rotation initiates from wind shear, differing wind speeds, directions at various altitudes, creating horizontal spin-tilted vertical by the storm's updraft. Not every mesocyclone produces a tornado. Rotation must tighten and extend downward, forming a funnel cloud that becomes a tornado upon ground contact. The process is delicate, influenced by pressure, moisture, and terrain. Some storms tease tornado formation for hours without producing. Others generate twisters abruptly. Tornadoes travel from near stationary to over 70 mph. Most are small and weak, EF-Frau, EF1 on the enhanced Fujita scale, but occasionally monsters emerge, EF4, EF5, capable of obliterating neighborhoods and hurling vehicles. 5. Based on damage. EF5 based on damage. EF5 branches. EF5 demolishes well-built houses. Tornadoes are most frequent in the United States Tornado Alley. Central Plains from Texas through the Dakotas, where Gulf of Mexico warm, moist air meets cold, dry air from the Rockies and Canada under expansive skies. But tornadoes occur globally on all continents except Antarctica. Waterspouts, tornadoes over water, are common off Florida and in the Mediterranean. Even the UK experiences several annually, typically mild. Now, let's turn to hurricanes, tornadoes' larger, longer-lived, more predictable cousins. Known as cyclones or typhoons regionally, these massive rotating systems form over warm ocean waters. They can span hundreds of miles and persist for days or weeks. While tornadoes are violent dancers, hurricanes are slow-moving atmospheric engines. Hurricane formation requires specific conditions. Warm ocean water, at least 79 degrees F to a depth of about 150 feet. A pre-existing atmospheric disturbance, e.g., thunderstorm cluster, and low vertical wind shear, strong shear can dismantle developing storms. When these align, warm water evaporates, moistening the air. As moist air rises, it cools, condenses into clouds, releasing latent heat. The same energy released in thunderstorms. This heat warms surrounding air, enhancing uplift. As air spirals inward due to the Coriolis effect, a low-pressure center forms, a tropical depression. With intensification and organization, it becomes a tropical storm. At sustained winds of 74 mil/s, it earns hurricane status. A hurricane comprises distinct parts. The eye, a calm, clear, low-pressure center with light winds. The eye wall, a ring of towering thunderstorms containing the strongest winds and heaviest rain, the most dangerous sector, and rain bands, spiraling bands of showers, storms extending outward hundreds of miles. Hurricanes are categorized 1-5 on the Saffir-Simpson hurricane wind scale based on sustained winds. Category 1, 74-95, damages roofs, trees, power lines. Category 5, 157 plus MPF, causes catastrophic destruction, rendering areas uninhabitable for weeks. Beyond wind, hurricanes bring storm surge, a sea level rise from winds pushing water shoreward, often the deadliest aspect, especially in low-lying coasts. Combined with torrential rain, sometimes over 2 feet, they cause widespread flooding and landslides inland. Interestingly, hurricanes serve a climate role, redistributing heat from tropics to poles, moving excess equatorial energy. Unlike tornadoes, hurricanes are trackable via satellites and models, allowing days of warning for preparation and evacuation. Yet their size and power make them formidable upon arrival. Eventually, hurricanes weaken over cooler water or land, deprived of their warm water fuel. Winds diminish, rains taper, leaving behind cleanup and memory. Despite their power, tornadoes and hurricanes are expressions of fundamental atmospheric principles. Symptoms of imbalance: heat redistribution, pressure equalization. They are not anomalies, but natural outcomes of forces maintaining atmospheric vitality. So, when you hear thunder or see swirling clouds from space, remember, these are Earth's most potent narratives, written in air and water. Turbulent, terrifying, yet astonishingly beautiful, reminding us of our sky's vibrant life. Wind is the unseen sculptor of our world, invisible yet palpable as it dances through hair, pushes leaves, and occasionally inverts umbrellas as a reminder of its authority. It is gentle and wild, playful and destructive, simply air in motion, refusing stillness. Fundamentally, wind arises from air pressure differences. When one area has higher pressure than another, air moves from high to low pressure to balance. The greater the difference, the stronger the wind. It's nature's tidying, though often untidy. Pressure differentials resemble hills and valleys. Air flows downhill, from high to low pressure. But unlike water, it doesn't move straight due to Earth's rotation. The Coriolis effect. As Earth spins, moving air is deflected right in the northern hemisphere, left in the southern, imparting curvature to winds and shaping global patterns. On a planetary scale, equatorial regions receive intense solar heating, warming the surface. Warm air rises, creating a low-pressure zone. This rising air spreads poleward aloft, then sinks around 30° N/S latitude, forming high-pressure zones. Descending air flows back toward the equator at the surface, generating steady east-to-west trade winds. These reliable winds propelled early sailors, fueling exploration, a blend of wind and ambition. Between 30–60 degrees latitude, winds reverse, west to east. As the westerlies, driving weather systems across North America and Europe. Near the poles, polar easterlies flow from the east, carrying frigid air toward mid-latitudes. This global circulation divides the planet into wind belts and jet streams. But wind is also intensely local, shaped by topography. Sea breezes exemplify this. On sunny days, land heats faster than water. Warm air above land rises, creating low pressure. Cooler ocean air rushes inland as a sea breeze. At night, the process reverses. Land cools faster, generating a land breeze. This rhythmic exchange is among nature's simplest, most soothing wind patterns. In mountains, wind assumes dramatic forms. Daytime anabatic winds. Air heated along slopes rises, drawing cooler air up from valleys. Nighttime katabatic winds. Cooled, denser air flows down into valleys. These diurnal shifts cause significant temperature swings, integral to mountain life. Some katabatic winds are famous, like the Mistral in southern France. A cold, dry wind roaring down the Rhône Valley toward the Mediterranean, exceeding 50 m/far, influencing climate and architecture, e.g., sheltered windows. In California, Santa Ana winds blow desert air coastward seasonally. Hot, dry, exacerbating wildfires by desiccating vegetation and fanning flames, met with awe and dread. A remarkable wind system is the Chinook, a snow eater, on the eastern Rockies slopes, where warm, dry air descends into plains, raising temperatures up to 40 degrees Celsius in an hour, like nature's hairdryer. Wind can be sneaky. Microbursts, powerful thunderstorm downdrafts, descend rapidly, spreading at ground level, causing tornado-like damage, hazardous to aviation. Dust devils, mini whirlwinds on hot, dry days from uneven ground, heating, are not tornadoes, but harmless columns of air and debris, common in deserts. At the other extreme, gales, sustained winds. 39 MPa and cyclones, intense low-pressure systems, bring hurricane-force winds, torrential rain, storm surges. Not all winds are violent. Some are persistent background players like jet streams, high-altitude, fast-moving air ribbons, steering weather systems, influencing flight times and seasonal trends. They flow west to east at 100 to 200 MPa, meandering like lazy sky rivers, forming at sharp temperature boundaries, e.g., polar versus mid-latitude air. Jet streams shift seasonally. Their undulations can trap weather systems, causing prolonged heat waves, rain, or cold spells. Despite invisibility, Wind profoundly shapes our world, transporting moisture, spreading seeds, carrying pollen, eroding rock into sand over millennia. It sculpts desert dunes and Arctic drifts, powers sailboats and turbines. It is both whisper and force. Historically, humans respected and relied on wind. Ancient mariners navigated by it. Farmers heeded its changes. Today, we harness it for renewable energy, turning blades for electricity, sans fuel. Wind also regulates temperature, carrying warm air from hot zones and cool air into warm areas. A breeze can be lifelike on a hot day, or bitingly cold in winter. Hence, wind chill, a measure of heat loss from skin, not actual temperature reduction. While wind may seem chaotic, it follows precise physical laws. Paths set by pressure gradients, shaped by topography, temperature, and Earth's spin. Whether rustling leaves or howling in storms, wind is a planetary language. So, next time trees sway or a breeze grazes your cheek, appreciate this silent, swirling presence. A constant companion, ever moving, reshaping our air. A clear sign. The atmosphere is alive, in motion, and quietly powerful. When winter arrives, it transforms the world decisively. Trees stand bare and still, ponds freeze like polished glass, air nips at noses. Snow drapes rooftops, muffles sound, paints landscapes in hushed white. Behind this serenity lies captivating science. Snow, ice, sleet, freezing rain are the icy signatures of the atmosphere's coldest moods. Let's start with snow, winter's icon. A snowflake begins high aloft as a tiny dust particle. Water vapor condenses directly onto it, freezing into an ice crystal. As the crystal drifts through clouds, more vapor condenses and freezes onto it, causing growth. Snowflake shape depends on temperature and humidity, constantly changing during descent, making identical flakes exceedingly improbable. Most exhibit hexagonal symmetry due to water's molecular structure, bonding at specific angles, creating symmetrical patterns, plates, needles, stars. Under microscopes, they reveal breathtaking geometric detail, sculpted solely by temperature and moisture. Snow is light but cumulative. A cubic foot of fresh snow weighs 5 pounds, depending on moisture. Millions of flakes can swiftly burden roofs and branches. Wet snow, higher in water content, is denser and heavier than dry, powdery snow favored by skiers. Not all frozen precipitation is as elegant. Sleet occurs when snowflakes fall through a warm layer, partially melting into droplets, then refreezing in a colder layer near the ground into ice pellets that bounce and create crunchy, slippery surfaces. Freezing rain is trickier. Snow melts completely into rain in a warm layer, then passes through a shallow, sub-freezing layer just above ground. The rain remains liquid supercooled until surface contact, instantly freezing into a thin, slick ice glaze. Beautiful yet hazardous. Freezing rain causes power outages as ice accumulates on lines and limbs, snapping them. Frost. Delicate ice patterns on cold surfaces during calm, clear nights. Forms when surface temperature drops below dew point and freezing, depositing vapor directly as ice crystals. The result is a thin white film coating grass, windows, windshields with feathery shapes. Rime ice, a related phenomenon, forms under specific conditions. Clear skies, calm winds, moist air, growing complex structures like needles or ferns, creating fairy tale landscapes. Unlike snow, frost doesn't fall, it grows in situ, like atmospheric sculpture. Under certain conditions, winter produces ice fog. tiny supercooled droplets freezing into minute ice crystals near the ground, creating dense, frozen mist common in extreme cold, e.g. Alaska, northern Canada, imparting a silvery glow and reducing visibility like regular fog but with a frozen edge. Wind exacerbates winter cold via wind chill, a real measure of heat loss from skin. Your body warms a thin air layer around it. Wind displaces this layer, forcing your body to work harder to stay warm. Faster wind equals faster heat loss and colder perception. For example, 20 degrees with 15 mVOF, wind feels like 5 degree F. Wind chill doesn't lower actual temperature, but accelerates frostbite or hypothermia risk, reminding us wind is not just summer's breeze, but winter's bite. Then come blizzards, winter's heavyweights. A blizzard isn't defined solely by snow, but by wind and visibility, sustained wind gusts. Me. Lasting can 3 hours. Blizzards can occur without new snow is blown into, yet they begin with basic ingredients: moist air, cold temperatures, atmospheric instability. In contrast, snow squalls are brief, intense snow and wind bursts, reducing visibility suddenly, lasting under an hour, causing rapid temperature drops and hazardous driving. Despite challenges, winter weather is crucial. Mountain snowpack provides essential spring. Meltwater, ice reflects sunlight, regulating Earth's temperature. Frost and snow insulate soil, protecting plant roots from extreme cold. So, when you see your breath or catch a snowflake, you're witnessing one of the atmosphere's most intricate performances. Each icy detail, from frost-tipped leaves to snow-blanketed fields, results from precise, elegant physics. Behind silent snowfall lies a story of temperature, motion, moisture, and time, narrated in flakes and wind. Some weather arrives subtly. No thunder, lightning, or snowstorm, just a gradual air thickening, a soft grey veil blurring the world, muting morning. This is fog, weather's most enigmatic child. It doesn't roar, it whispers, swirls, transforms familiar into unknown. While seemingly simple, fog embodies subtle science and quiet complexity. Essentially, fog is a ground-level cloud, forming when water vapor condenses into tiny liquid droplets suspended near the surface. These droplets are too small to fall as rain. Instead, they float, scattering light, limiting visibility, creating a closer, quieter, dreamlike world. Fog types vary by formation mechanism, influenced by temperature, humidity, terrain, time. Radiation fog, the most common, forms on calm, clear nights as ground cools rapidly, chilling adjacent air. If moist air cools to dew point, condensation occurs, forming droplets. This fog often settles in valleys, low-lying areas where cool air pools, typically in early morning hours before sunrise. Delicate, it dissipates with breeze or morning sun warmth, evaporating like a drawn curtain. Advection fog forms from air mass movement over differently tempered surfaces, e.g. warm, moist air blowing over cold coastline. The cold surface cools the air to dew point fog forms. It can blanket large areas, persisting all day if cooling continues, common along coasts, evoking seafaring novels and lighthouse tales. Upslope fog occurs in hilly mountainous terrain when moist air is forced upward along slopes. As air rises, it cools adiabatically, lower pressure at altitude, reaching dew point, forming fog. Unlike radiation fog, It can occur day or night, lingering until wind shifts. Evaporation fog, steam fog, forms when cold air moves over warmer water, seen over lakes, rivers, hot tubs on chilly mornings. Warm water evaporates into cold air, increasing humidity, causing immediate condensation into rising, curling fog wisps. Ghostly, delicate, fleeting. Freezing fog is dramatic, air temperature below freezing, but fog droplets remain supercooled liquid. Upon surface contact, tree branches, cars, wires, they freeze instantly, forming rime ice. A rough, milky white ice coating, creating surreal frosty worlds. Unlike frost, direct vapor deposition, rime forms from frozen droplets, building rapidly, hazardous for road aircraft, yet sculpting everyday objects into ice art. Not all fog is equal. Mist resembles fog, but is less dense. Visibility 1 km 6 miles is mist, below is fog. Mist feels lighter, more suggestion than event, but forms similarly. Haze looks fog-like, but stems from dry particles. Dust, smoke, pollution, scattering light differently, yielding a dull, washed-out sky. Haze isn't damp, doesn't require specific humidity temperature, but affects visibility, mood, breathing. Fog alters sound. In dense fog, sound waves scatter and muffle, making noises seem closer farther, adding mystery blurring senses. Fog also plays with light. Headlights reflect off droplets, creating glare. Hence, fog lights are mounted low to beam under the densest fog. Fog holds cultural emotional weight, featured in poetry, film, mysteries, evoking peace, ominousness, romance, eeriness. It invites pause, closer looking, slowing down. Behind softness and symbolism lies solid science. Dew points, condensation, temperature gradients, air movement. Fog may be nature's quietest weather, but it leads a rich, active life. Next time you wake to a fog-wrapped world, step outside, feel the dampness, watch the air seem to breathe. You're inside a cloud, not skyborne but at your feet. Weather at its most intimate, a gentle secret suspended between air and water, visibility and imagination. Sometimes weather lacks drama. No thunder, lightning, swirling snow. Instead, it creeps in slowly, elevating temperatures degree by degree until everything feels heavy, sluggish, too still. Welcome to heat waves and droughts, where air hangs thick, soil cracks, and breezes feel toaster-warmed. Let's begin with heat waves, prolonged periods of abnormally hot weather, often with high humidity. A heat wave isn't a few hot days, but significantly above. Average temperatures for a location and season, typically lasting 3 days. Some persist weeks, reinforced by stagnant high-pressure systems. Heat waves stem from high-pressure systems, ridges on weather maps acting as atmospheric lids. Air under high pressure sinks, warming adiabatically, suppressing clouds, allowing unabated sunlight. Day after day, heat accumulates. Urban heat islands amplify this. Cities with concrete asphalt absorb more heat, release it slower, keeping nights warmer than countryside, where vegetation and soil release heat efficiently. Humidity critically influences heat perception. In humid conditions, sweat evaporates slowly, impairing the body's cooling, making you feel hotter than actual temperature. The heat index quantifies this. E.g., 95 degree F with 55% humidity feels like 11 degree F, the kind of heat that softens asphalt and questions genes. Prolonged heat exposure risks heat exhaustion, stroke, especially for the elderly, children, those with pre-existing conditions, leading to spiked emergency visits during major heat waves. Cooling centers, shade, fans are vital. Droughts are heat waves, slow, silent counterparts, prolonged below average rainfall causing water shortages. They begin unobtrusively when rain ceases, lasting weeks to years, with effects varying by region: shrinking rivers, cracked soil, depleted reservoirs, stressed crops. Severe droughts cause famine, forest die-offs, migration. Drought is measured meteorologically, precipitation lack; agriculturally, soil moisture; crop impact, hydrologically, low water levels; socio-economically, water shortages affecting economy, society. Causes include atmospheric patterns, El Niño, La Niña, disrupting rainfall; persistent high pressure; ocean temperature shifts; climate change. Drought links to rising temperatures. Increased evaporation rates deplete soil, lakes, vegetation moisture. Intense post-drought. Rain may run off hardened soil, causing flash floods instead of replenishment. Heat waves and droughts often interact cyclically. Drought dries land, reducing evaporation, allowing temperatures to climb further. A feedback loop, locking regions into dry, sweltering conditions. Despite challenges, both are natural climate components, occurring for millennia, though recent decades show increased frequency intensity in many areas, partly attributed to climate change. A warmer atmosphere holds more energy, making extremes likelier. Adaptation is growing. Cities implement green roofs, tree canopies; farmers use drought-resistant crops; efficient irrigation; water conservation becomes essential. Even in aridity and heat, beauty persists. Cracked earth patterns, wind-blown grasses, trees defiant under harsh skies. Heat waves yield fiery sunsets through shimmering horizons. And when rain returns after drought, it's a homecoming, not merely weather. So, when air is still and heat settles, take a slow breath. You're witnessing weather's quieter side, not flashing or rumbling, but reshaping in silence. Heat and dryness may lack storm headlines, but their effects are profound, etched into soil, memory, and the atmosphere's endless balancing narrative. Some weather dazzles with sound and fury, roaring winds, pounding rain, blinding snow. Others enchant rather than overwhelm, appearing in storm aftermaths or when sunlight and moisture align perfectly. These are the atmosphere's gentle wonders, optical illusions and subtle spectacles reminding us the sky is an artist at heart. Let's start with the quintessential wonder, the rainbow. A rainbow isn't tangible or reachable, it's an optical meteorological phenomenon, a light and perspective trick. Sunlight entering raindrops refracts, bends, reflects off the drop's back, refracts again upon exit. This bending splitting separates light into constituent colors: red, orange, yellow, green, blue, indigo, violet. Each refracting slightly differently, red least, violet most, forming a color circle. We usually see a semicircle. The ground obstructs the full circle, though airborne or high-altitude viewers might glimpse it. A primary rainbow always appears A42 degrees from the anti-solar direction, sun behind you, rain mist ahead. Thus, you can't reach a rainbow. It moves with you. Each observer sees a unique version from light entering their eyes, personal as a fingerprint but made of light. Double rainbows sometimes occur, a second, fainter arc outside the primary from light, reflecting twice inside droplets, reversing color order, red inside, violet outside. Between the arcs lies Alexander's dark band, named for ancient Greek philosopher Alexander of Aphrodisias. When sunlight interacts with ice crystals instead of rain, halos, sundogs, and light pillars emerge. Halos bright, often rainbow-edged circles around sun-moon. form when light passes through hexagonal ice crystals, bending at 22 degrees. They resemble celestial crowns, common in cold weather with ice-rich upper atmospheres. Sundogs, parhelia, are bright spots flanking the sun, often within a halo, resembling colorful sun duplicates, vivid when sun is low. They require precisely oriented ice crystals, acting like tiny mirrors. Light pillars, vertical light beams shooting upward from sun or streetlights, result from flat plate ice crystals falling slowly, reflecting light into columns, appearing otherworldly, sci-fi-like sans aliens. Another gem is the glory, a series of colored rings around the observer's shadow cast onto cloud fog, often seen from airplanes when the aircraft's shadow is surrounded by shimmering rings on clouds below, caused by backscattered light interacting with tiny droplets. The pilot's glory. Coronas are related. Tight, colorful rings around sun-moon from light diffracting around individual water droplets in thin clouds. Mist, smaller and closer than halos, often pearlescent. Then, crepuscular rays, God rays. Sunlight beams radiating from the sun during sunrise. Sunset, when clouds scatter light. The rays appear to fan out, but result from perspective. Like converging railroad tracks, light streams through cloud mountain gaps, illuminating air particles, dust, moisture, pollen, with light-shadow contrast creating divine magical impressions. Venturing into twilight, the green flash. A rare event at sunrise, sunset, when the sun's upper edge appears green briefly. This occurs because the atmosphere acts as a prism, bending sunlight. Blue-green light bends more than red-orange, and, under right conditions, the last sun sliver appears green. Blink and miss, but cherished by sailors, sky watchers. Lunar rainbows, moonbows, are rainbows from moonlight. Fainter due to weaker moonlight, they require near full moon, rain mist, low moon behind observer. They appear white-silver, but long exposure photography may reveal pale colors. These phenomena remind us light and atmosphere constantly interact. We don't always notice, but under right conditions, the sky becomes an optical marvel. Canvas, subtle or bold, fleeting or enduring. No special equipment needed, just curiosity, upward gaze, and patience for perfect light, moisture, timing alignment. Whether a post-storm rainbow, wintry sun halo, or faint glory around your airplane's shadow, each whispers from the sky, reminding us nature speaks not only in thunder lightning, but also in color, shimmer, light bending through air water. Weather shapes the world, light paints it. Occasionally, the atmosphere becomes not just a system, but a gallery. Weather can be intensely local. Sunshine for you, rain for a nearby friend. Yet it's wonderfully global, varying wildly by geography, latitude, ocean currents, elevation. From humid monsoons to swirling sandstorms, each region has a unique climate signature. Let's talk global weather and how the same sky behaves differently worldwide. Begin with the monsoon. A major seasonal weather system, monsoon, derives from Arabic mawsim, season, denoting seasonal wind reversals, bringing precipitation shifts. Most associate monsoons with heavy rain, but they're large-scale wind patterns driven by land, sea temperature contrasts. South Asia's monsoon is powerful. Summer land heating creates low pressure over the subcontinent. Moist Indian Ocean air rushes in, rising over Himalayas, condensing into prolonged rainfall. Essential for crops, rivers, aquifers, it also brings floods, landslides, disruption. Still, it's welcome after pre-monsoon summer heat. East Asia, Southeast Asia, Northern Australia experience similar patterns with timing intensity variations. The East Asian monsoon brings wet summers, dry winters, Australia's wet season, December. March features tropical storms, torrential rain, dramatic lightning. Desert weather thrives on extremes. The Sahara, largest hot desert, sees daytime temperatures 120 degrees Celsius, nights dropping 40-50 degrees Celsius due to dry air, lack of vegetation, rapid radiative cooling. Deserts host dust storms. Haboobs, towering dust walls from thunderstorm, downdrafts pushing dry soil sand into air, blotting sun, coating everything in grit. Australia's deserts experience similar. American Southwest dust storms peak in late summer with thunderstorms. Polar weather, ruled by ice, wind, extreme light cycles, features perpetual winter darkness, frigidity, and summer midnight sun. Katabatic winds. Cold, dense air flowing downhill from ice plateaus define polar regions, reaching hurricane force in Antarctica, sweeping snow in whiteouts. Polar regions are technically deserts. Low precipitation. Most snow fell millennia ago. Snow, when it occurs, is tiny ice crystals drifting gently. Tropics near equator. Amazon, Congo Basin, Southeast Asia, host rainforests with consistent heavy rainfall. Convectional rainfall dominates. Intense solar heating causes rapid air rise, afternoon cloud towers near daily thunderstorms. Short, intense, nourishing biodiversity. Consistent weather supports dense vegetation, layered canopies, teeming life. Savannas, farther from equator, have seasonal rainfall, long dry spells, wet bursts, shaping grassland ecosystems where grazing animals roam. Rain timing is critical. Island nations, especially Pacific, experience trade winds, tropical cyclones, ocean currents. The El Niño Southern Oscillation, ENS, a CCK, significantly influences global weather. El Niño shifts warm Pacific waters eastward, disrupting rainfall across Americas, Australia, Asia, Africa. La Niña brings cooler waters, opposite shifts. Ocean currents, e.g., Gulf Stream, Kuroshio, transport warm water tropics to poles, regulating coastal climates, e.g., UK's mildness versus similar latitudes. Mountainous regions, Andes, Himalayas, Rockies. Sea orographic precipitation, air rising over windward slopes cools, loses moisture, causing rain snow. Leeward rain shadows experience descending, warming, drying air. Aridity, e.g., Atacama. Desert west of Andes, among Earth's driest. Coastal areas have moderated temperatures. Milder winters, cooler summers, inland areas experience greater seasonal swings. Central Asia has scorching summers, bitter winters. Coastal Norway, warmed by Gulf Stream, has mild winters despite far north. Microclimates add variety. Shady ravines stay cool. Moist, sun-baked hills. Heat, city skyscrapers create heat islands. Vineyards on different slopes yield varied grapes. Every region has a weather signature from unique latitude, terrain, ocean proximity, atmospheric patterns. Yet underlying principles remain. Heat rises, moisture condenses, air moves high to low pressure. From driest desert to wettest rainforest, rules are consistent, outcomes diverse. So, wherever you are, watching tropical lightning, enduring desert dust storms, or standing in polar night snow, you're experiencing one version of a global story told in wind, water, sunlight, shadow, woven through Earth's every corner. We've explored weather's nature, but how do we predict incoming storms or sunny laundry days? Weather forecasting may seem guesswork, but is a refined art based on physics, data, meticulous observation. one of humanity's most complex regular tasks and immensely helpful. Start with present observation. To predict future, meteorologists need current global conditions, as weather is interconnected. A Texas thunderstorm may influence New York or Europe. Tools include global weather stations, recording temperature, humidity, wind, pressure, precipitation. Some automated, some human. Monitored, transmitting data to central databases regularly. Weather balloons, radio sondes, launched twice daily globally, carry instruments measuring atmospheric conditions vertically to 20 miles, crucial for understanding temperature, humidity, wind profiles, determining stability. Satellites revolutionized forecasting. Orbiting Earth, they provide continuous imagery, data. Geostationary satellites remain fixed relative to Earth, constantly monitoring same areas. Polar orbiting satellites sweep pole to pole, imaging the entire planet gradually. They track clouds, sea temperatures, hurricane formation, moisture, volcanic ash, wildfires, snow cover. Weather report animations often use satellite data. Radar is critical, especially short-term. While satellites offer space views, radar scans horizontally. Weather radar emits radio pulses bouncing off precipitation. Return signal. Strength, timing, reveal precipitation location, intensity, movement. Doppler radar detects storm motion, invaluable for identifying rotating thunderstorms potentially spawning tornadoes. All this data, billions of daily points, feeds numerical weather models, computer programs simulating atmospheric behavior via physics laws. They divide the world into a 3D grid. Each cell represents an atmospheric volume where models compute temperature, pressure, moisture, wind changes over time based on surroundings. The process is immensely complex, run on supercomputers solving equations for atmospheric dynamics, thermodynamics, radiation, cloud formation, etc. Major models include USGFS, Global Forecast System, European, ECMWF, European Centre for Medium-Range Weather Forecasts, UKMED. Each has strengths, weaknesses, specialties. Despite sophistication, forecasts retain uncertainty. The atmosphere is chaotic. Minor initial condition differences yield vastly different outcomes. Butterfly effect. Brazil. Butterfly flapping potentially causing Texas tornado. To manage this, meteorologists use ensemble forecasting, running models multiple times with slightly varied initial conditions, producing outcome ranges analyzed for most likely scenarios. Agreement among runs indicates high confidence, divergent signals unpredictability. Human expertise remains vital. Meteorologists interpret model outputs, compare models, incorporate local knowledge, e.g., mountain wind funneling, coastal fog generation, refining computer suggestions. Forecast accuracy has improved dramatically. Today's 3-day forecast matches 1980s. 1-day accuracy. 5-day forecasts are reliable. 10-day forecasts show trends, albeit less precision. Further out, uncertainties multiply, blurring events, timing, location. Short-term forecasts, nowcasting, predict rapidly evolving events. Thunderstorms, tornadoes, using high-resolution radar, local observations, frequent model updates, issuing watch warnings for safety. Probabilistic forecasting grows, e.g., 70% chance of rain versus it will rain. Reflecting forecast nature, likelihood, not certainty, aiding decision, making umbrellas, picnics. Forecasting is crucial for aviation, shipping, agriculture, emergency management, energy. Airlines plan routes, avoid turbulence, farmers schedule irrigation, utilities adjust for heat-cold. Emergency responders prepare for hurricanes, floods, wildfires. Machine learning, artificial intelligence are emerging tools, analyzing vast data, spotting patterns, improving models, complementing, not replacing, traditional forecasting. And you participate. Smartphone apps enable crowdsourced weather reports, filling gaps between official stations, providing detailed ground snapshots. So, next time you check a forecast showing 72 degrees F, 20% shower chance, remember the infrastructure. Orbiting satellites, high-flying balloons, supercomputers solving billions of equations, meteorologists interpreting data, and possibly you noting breeze changes. It's staggering collaboration, a global effort to read the sky. While we can't control weather, our understanding and prediction capabilities have never been better. Weather is ever-changing. Sometimes gentle, sometimes fierce, always dynamic. But recently, we've noticed something remarkable. Weather itself is transforming, not daily or seasonally, but over long periods. Central to this is climate change. To grasp climate change's weather impact, distinguish climate from weather. Weather is atmosphere's mood, today's tomorrow's conditions, rain, heat, breeze. It's short-term, local. Climate is atmosphere's personality, average moods over 30+ years, indicating regional norms, spring rainfall, winter cold, storm frequency. Climate has never been static, historically fluctuating between ice ages and warm periods from natural cycles, orbital shifts, volcanism, solar output. But current changes are different, faster, primarily human-driven. Since late 19th century, global average temperature rose 2 degrees F. Seemingly small, but for Earth's sensitive climate system, it's significant. Warming stems largely from greenhouse effect, natural process where gases, carbon dioxide, methane, nitrous oxide, water vapor, trap atmospheric heat, maintaining habitable temperatures. Carbon dioxide is key, released burning fossil fuels, coal, oil, gas. Deforestation reduces CO2 absorption. Rising greenhouse gas concentrations trap more heat, warming the planet. This warming doesn't just mean hotter summers, it alters global weather patterns. Heat waves are becoming more frequent, severe, prolonged. Previously, 20-year events now occur every few years or annually, amplified by urban heat islands. Nights warm faster than days, reducing relief from daytime heat, increasing human, crop, animal stress. Precipitation patterns shift, some areas wetter, others drier. Warmer air holds 4% more moisture per 1 degree F rise, intensifying rainfall events, downpours overwhelming drainage, causing floods. Yet, increased atmospheric moisture doesn't guarantee universal rain. Some regions dry further, especially drought-prone areas. Longer dry spells plus higher temperatures. Parched soils shrink rivers, stress ecosystems. Southwest, US, Southern Europe, parts of Africa experience more frequent, severe droughts. This pattern, wetter areas, wetter, drier areas, drier, is a climate change. Hallmark, not simple warming but system-wide reshuffling. Storms are changing. Warmer oceans fuel tropical storms, potentially strengthening hurricanes, cyclones, typhoons. Evidence suggests storm numbers haven't risen dramatically, but intensity has. More. Category 4-5 hurricanes, capable of catastrophic damage, carrying more moisture, increasing rainfall upon landfall, e.g. hurricanes, Harvey, 2017, Florence, 2018. Winter storms are affected. Warming doesn't eliminate snow. Increased moisture can boost snowfall in some regions, but snow seasons start later, end earlier. Snowpack shrinks, impacting water storage. Climate change alters jet streams. Arctic amplification. Arctic warming faster than globe reduces pole-equator temperature difference, weakening jet streams, making them wobble. Slower, wavier jet streams stall weather systems. Rainstorms linger, heat waves lock, linked to recent extremes, European heat waves, US flooding. Sea level rise. Up 8 inches since 1800s. From melting glaciers, thermal ocean expansion exacerbates storm surges. Tidal flooding, reaching farther inland, affecting more people. Climate change influences wildfires indirectly via conditions, hotter temperatures, drier soils, earlier snowmelt, lengthened fire seasons. Lightning may increase with more convection. Winds, dry vegetation spread fires rapidly. Result: more intense, frequent, damaging wildfires. Globally, California, Australia, Siberia. Not every weather event is climate change caused. Weather will always vary. Cold snaps, rain, mild seasons persist. But scientists now study how climate change raises specific event likelihood, intensity, attribution. Science. Understanding how warming background conditions shape atmospheric delivery. What can be done? While some warming is inevitable from past emissions, future outcomes depend on current choices, reducing greenhouse gases, switching to renewables, improving efficiency, protecting forests, altering agriculture land use. Adaptation is key. Communities redesign infrastructure for heavier rain, plant trees for cooling, update building codes for stronger storms. Farmers use drought-resistant crops. Cities map flood zones, build seawalls. Individuals learn heat safety, water conservation, carbon footprint reduction. Small actions matter. Walking instead of driving, turning off lights, supporting environmental policies. Collectively powerful as raindrops in a storm. Weather remains capricious, beautiful, unpredictable in details, but its canvas is changing. Boundaries shifted, stakes raised. We are both observers and participants. So, when skies darken unexpectedly, summers feel prolonged, or rains intensify, remember, you're witnessing not just weather, but a planet in transition. A story written by wind, water, humanity, still within our power to shape. Thus, we've journeyed through winds, rains, clouds, and silent snow. We've explored lightning, illuminated skies, desert stillness, and invisible forces guiding global weather. From gentle fog to immense hurricanes, sunlight science to wind whispers, we've glimpsed how this beautiful, chaotic, ever-moving system operates. Weather is more than background. It's a conversation among earth, ocean, sky, a language of temperature, moisture, motion, written in clouds, spoken in thunder. It molds our landscapes and lives, bringing harvests and hardships, calm and chaos. Despite our technology, it still surprises. As you rest tonight, the atmosphere persists. Wind flows over peaks. Raindrops gather on leaves. A snowflake forms afar. It's comforting that the sky never truly sleeps. It shifts, reshapes, continues its slow dance above. Before we part, I ask again, where are you listening from? What time is it there? Midnight, 2 a.m., a quiet afternoon with drawn curtains. Wherever, whenever, thank you for joining this deep science sleep journey through weather science. If you found this calming, intriguing, or slightly magical, please consider liking or subscribing. It helps others find their way here and means much. Now, rest well. Let thoughts drift like clouds, and may dreams be soft as fog and bright as a rain-cleared morning.